Okay, I'm going to go ahead and get started. There's nobody here but me, but that's okay. We were talking about this last time. The human body is in a constant balancing act, trying to make sure that there's proper nutrients in the system, that there is enough fluid in the system, that there's enough salt in the system. And it's just a constant balancing act. The amazing thing is that it gets out of balance so infrequently. And it's the same way with the human mind. If we're talking about counseling, if we're talking about somebody with a mental illness, what we're dealing with is an individual who has feelings that are negative enough that it's disrupting their lives. Normally, if we have an individual with a mind problem, such as depression or anxiety, the human body will try to bring it back to a point of homeostasis, of a point of hojo. Here I am using a Navajo word, a point of balance. So if you're depressed, you can't stay depressed for very long because the human body won't allow that to happen. What will happen in the brain is that if you are depressed, it will increase the number of serotonin receptor sites. And that way, of course, because there are more serotonin receptor sites, whatever minimal amount of serotonin there is out there is at least attaching itself to a receptor site. So it's very difficult to actually be depressed for an extended length of time because the human body won't allow that to happen. It's not balanced. It's the same way with salt and water. If you're not taking in enough water, your salt level will increase. The human body will tell you, your body will tell you what you need. If you're missing a mineral, if you're missing a vitamin, then the human body will crave that vitamin. It'll crave you taking in that vitamin. Let's say, I don't know if you've ever had any cravings or not, but if you craved a salty food, you saw a bag of potato chips and you just had to have it because you were starving for potato chips. Well, you probably weren't starving for the chips, you're probably starving for the salt, and your balance was just a little bit off. So then you eat your bag of potato chips and then all of a sudden you're thirsty, which makes me thirsty just thinking about it. Anyway, so you're thirsty. The reason you're thirsty is because you need to balance out the amount of salt that you've taken into your body. And there you go. Some people don't like salt. Some people don't eat very much salt. Other individuals crave it constantly. Those individuals are the ones that retain water. If you retain water, then you crave salt. If you don't retain water, then you do crave salt. Don't retain water. Okay, well, anyway. And there are different types of individuals. Once upon a time, as they decided to bring slaves over from Africa, they would put masses of them on boats. And of course, they didn't have enough water. They didn't have enough food for these individuals. So a lot of times they would starve them, and they wouldn't have enough salt. The ones that survived were the ones that didn't need a lot of water. In other words, they were the ones that had who didn't retain salt. Because of this, a lot of the individuals in the United States, African Americans, people of African descent, individuals whose ancestors were brought over here as slaves, the ones that survived the trip over were the ones that were sensitive to salt. They didn't need a lot of water. They didn't take in a lot of salt. So these individuals now, because of their ancestry, these individuals, of course, have high blood pressure, and they don't know it. You don't know when you have high blood pressure. there nothing happens. It's not like blood vessels in your eyeballs burst or you start bleeding from the nose. So if you have high blood pressure, it's one of those silent killers. So nobody knows it unless you take your blood pressure. And there's a lot of African Americans. There's a higher percentage of African Americans with high blood pressure than just about any other group. Because we're constantly burning fuel, utilizing and breathing out liquid, and entering into different environments, the process of maintaining homeostasis is a constant balancing act. Losses that we must have, that we cannot get around, are known as obligatory losses, and they obviously require constant monitoring of primary need levels. You've got to get from this place to that place, where you're going to have to walk. Well, when you walk, of course, your muscles are burning fuel. You are dehydrating because you're breathing out a little bit deeper than you were before. So you're going to need water, and you're also going to need fuel in order to get from here to there. And those are obligatory losses. Cooling not only slows the action of molecules, we're talking about temperature regulation now. Cooling not only slows the action of molecules, but it slows the chemical reaction in cells as well. Enzyme systems in most mammals and birds are most efficient at normal temperature. For humans, of course, it's 98.6. For dogs, it's a little bit hotter than that. Their normal temperature runs in just over 100 degrees Fahrenheit. But we as humans, we're about 98.6. I've been hospitalized, not a lot, but from time to time I've hurt myself. I had ruptured spleen at one point. Anyway, I've been in the hospital several times, and it turns out that my normal body temperature is closer to 96.8 than 98.6. My body is a little cooler than most people. I guess that makes me a cold-hearted person, but anyway, it's in the 96 degree range. If we took my temperature right now, it'd be right around probably 96.8, 97, something like that, which is almost 2 degrees cooler than humans are supposed to be. That the average human is. If we took what they did is they took a number of individuals, they took the temperature, and what they determined was that the average temperature was right around 98.6. Doesn't mean you have to be at 98.6. If I had a temperature of 98.6, I'd have a fever. So what they have actually done is just averaged it out. Some people have 96, some people have closer to 100 degrees is their temperature, normal running temperature. So the average is 98.6. Any higher temperature and protein molecules do not bind properly and thus cannot function as they should. And we know when this takes place. If somebody has a fever, a lot of times what will happen is the individual will go into seizures. The reason they're going into seizures is because the cells in their brain are starting to break down, and the protein in their brain cells is starting to break down. This is one of the reasons why measles is such a big killer. You can't give somebody with the measles aspirin. If you give them aspirin, then they may have a reaction called Rise syndrome, where they go into a coma. So it's very difficult to bring down somebody's temperature if they have the measles. A lot of times you have to put them in ice baths. You have to give them alcohol washes that draw the temperature off. So that's one of the reasons why the measles were such a big killer when it came to the Americas. Killed off, along with smallpox and a lot of other diseases from Europe. It killed off a lot of people. But the fever, of course, the measles was one of the big killers of indigenous peoples in the Americas, unfortunately. At very high temperatures, the amino acids in the proteins break apart and begin to fuse together at random. This isn't good. The protein in the brain is especially susceptible to high temperatures, and this is one of the reasons why temperature above 101 degrees, of course, is fairly destructive. Individuals who have relatively low temperatures, of course, if I had a 98.6, I would be sick. But if my temperature went over 101, I still have that difference between the proteins aren't going to start breaking down until you get into the 105, 106 range. But of course, measles, of course, will give you a temperature that high. Prolonged high fever can cause brain centers that regulate heart rate to die, and of course, if that ever happens, then the patient dies. At very low temperatures, the cellular membranes are disrupted by the formation of ice molecules, and even when thawed, they cannot reform properly. I was watching a football game this weekend, and the announcer's brother was in the Arctic Ocean. I don't know what he was doing up there, but of course there's always a possibility if you get into that kind of a situation where it's below zero temperatures that you're going to get frostbite. The reason frostbite destroys tissue is because it freezes the cells. I had frostbite in my ears when I was younger. I lived in Indiana, which is not always that cold, but sometimes the temperature would go below zero. I can remember at one point when I was in college, I was going to work one morning and the temperature was like 25 below zero. And I had to walk about a half a mile to work. By the time I got to work, I was pretty cold. I had covered up fairly well, but of course there are parts of your body you can't cover up very well. Anyway, when I got there, I took off my coat and I started getting to work and warming up, of course. All of a sudden my nose started bleeding. What had happened, I had frozen the inside of my nose and it burst the blood vessels in my nose, and I started having a nosebleed. Warm-blooded animals generate heat from the inside and keep themselves warm, and thus they are referred to as endotherms. This is the way that horses, woolly mammoths, of course they have all that thick hair, and they will grow a thicker mass of hair in the wintertime in the cold regions. Lots of horses up in Montana, lots of cows up in Montana. If you look at a horse from Montana, one of the things you'll see is that their hide, they have an under fur. They grow an extra layer of fur in the wintertime to stay warm. We had horses when I was in Montana. In Montana, and what we would do in the wintertime, we would give them extra feed. Usually it was fairly rich feed. We give them oats, and we would also give them hay. They can live off of hay, but the richer feed allows them to create more heat. So what they would do, we had a pole barn, which is a three-sided barn. They would go into one corner and they would just stand there and generate heat between the two of them, and they were nice and cozy, no matter how cold it got. And it got really, really cold up there for extended lengths of time. Sometimes it was negative temperatures for weeks on end. Yeah. Anyway, so we would give them, we would not only give them hay, but we also gave them oats, and they were able to generate their own heat. There are a lot of cattle up there, and the cattle usually are out. They're not in barns, so the cattle will eat. They have to feed them, and that's why they roll their hay. They can just give the cattle rolls of hay. Endotherms generate heat by burning food in the blood and the body, a process known as metabolism, of course. Heat inside the body is measured in kilocalories. Kilocalorie is one kilocalorie is enough heat to raise the temperature of 1 liter of water 1 degree centigrade. If you've ever been on a treadmill, It will tell you how many calories you are burning. What they're really talking about is kilocalories. So as you're running along every 30 or 40 seconds, you will burn one more calorie. And what they're telling you is that you have generated enough energy to raise the temperature of a liter of water 1 degree centigrade. An adult can burn as many as 600 kilocalories per hour with strenuous exercise, but only 60 kilocalories when resting. So if we're watching television, sitting there watching television, every hour you're burning about 60 kilocalories. As interesting as that may be or may not be. Of course, if we're, I don't know, digging a ditch and we work for an hour and we're using our muscles and we're sweating like crazy, potentially we're burning as much as 600 kilocalories per hour. Or you're running a marathon. If you're running a marathon, you're probably burning that many calories. At rest, the brain accounts for 1/3 of the heat generated by the body. The human brain, of course, is relatively large, and because of that, we burn a lot of energy. If we're thinking, usually we are, if we're awake anyway. As activity increases, the brain continues its level of heat production, but the muscles can increase their heat production tenfold. So the brain, of course, the more you're thinking, the more heat that it's generating. But your muscles, of course, if I ran this weekend, so I'm jogging along the trail, I was burning, probably it wasn't tenfold, but I was burning some fairly interesting calories. I lifted on Friday, and of course when you lift and you do all that strenuous exercise, your muscles all of a sudden are a lot hotter. It's really kind of interesting because different groups of individuals will burn energy differently. As a Caucasian, potentially my ancestry developed in a cold climate, and because of that, when I exercise, I sweat a lot. I sweat a great deal, mainly because potentially my ancestors developed in an area that was not only relatively cold, but there was adequate water. So my ancestors didn't really have to worry about where to find the next drink of water. Not only that, but of course because of of who we are and where we developed, we sweat a lot. And so if you're ever around white people, Caucasians, you probably notice that they sweat a lot. People from a warmer climate, like people from that evolved around the equator, these individuals don't sweat nearly as much because, of course, when you're in that kind of heat, if you sweat a lot, then you're going to require a lot more water. And you're also going to require a lot more salt because when you sweat, of course, you're sweating out salt. So individuals who evolved in the European climate, which is relatively cold. Of course, there was the Ice Age, and that area was covered with ice. So was most of North America was covered with ice. They evolved in a cold climate, and so they are different. If you look at me after I've been lifting for 15 or 20 minutes, I'm pretty wet. I'm sweating pretty good. Other individuals who are doing exactly the same exercises that I am, they don't sweat nearly as much. As interesting as that is. Humans can create heat by increasing metabolism, by breaking down brown adipose tissue, by shivering, and by increasing blood flow by constricting blood vessels. It's cold outside right now, so if you go outside and stand there for a while without adequate cover, you'll start shivering fairly quickly.
The first thing that happens in your body is you will increase your metabolism. Your body starts to burn heat, burn energy stores a little bit faster so that it generates heat. The next thing that will happen is you'll start shivering. Shivering, of course, has to do with muscle movement. And because the muscles are being activated, you're starting to generate heat just from the activity. And then, of course, it can increase blood flow by constricting blood vessels. Your blood vessels will get smaller, and this is one of the reasons why your hands get so cold, because of constricted blood flow. That's why when I get cold, my ring falls off. I have a ring on my ring finger, and if it gets really cold, of course the blood vessels are constricted. It pulls in the fat tissue around my finger, and my ring falls off. Sometimes my wedding ring falls off, which is kind of dangerous. Anyway, the last thing that will happen is you'll start breaking down brown adipose tissue. Brown adipose tissue is really kind of interesting. It's found around your vital organs, in your thorax, and around the cervical and thoracic levels of your spinal cord. So this is the fat that is around all of your organs. No matter how skinny you are, no matter how much body fat you maintain, you're still going to maintain some degree of brown adipose tissue. Some individuals are so sedentary that they will accumulate a lot of brown adipose tissue around their organs. This can be dangerous because if you get brown adipose tissue, if you start collecting fat around your heart, then it can actually squeeze your heart so that it becomes less efficient. This is normally what happens in congestive heart failure. Your heart is being strangled by the fat around it, or it's beating inefficiently for another reason, a leaky valve or whatever. And this is usually what causes congestive heart failure. Congestive heart failure is really kind of interesting. Congestive heart failure, your heart's not beating properly, and because your heart's not beating properly, you're accumulating fluid in your lungs because it can't get rid of all the fluid that is building up in your lungs. And so eventually you drown in your own fluids because you can't get rid of it. Usually before that happens, of course, your ankles will swell up. You'll get what we refer to as edema. Edema means fat buildup or water buildup, actually. And we can draw that off by giving you a medication that draws off fluid, like Lasix is the traditional one. They have new diuretics out there. Lasix is the one that I remember. It's the one that my dad used when he had congestive heart failure. My dad had a faulty valve in his heart. He actually had a couple faulty valves in his heart. He had to have open heart surgery a couple different times. One time was right around Labor Day. And he was getting worse and worse and worse, and it was right around Labor Day, and they told him, well, as soon as the holidays are over with, we'll go ahead and give you surgery. We'll go ahead and do surgery and fix that valve for you so that you don't die. Well, he got worse. It was Friday. It was on Friday. He got really bad on Friday, and you could hear him. You could hear his breathing. Sounded like he had pneumonia. Of course, he didn't have pneumonia. What he had was this fluid buildup in his lungs, and you could actually hear it. And of course, my mother's a nurse, and she decided, well, those sons of bitches, those damn doctors, I'm just going to let him die, and that'll show these guys. Of course, it wouldn't have showed them anything, except that they made a mistake. So I can't remember where, I think I was in Nebraska. Anyway, I drove over to Muncie, Indiana, which is about a day's trip, to see my dad. And when I got there, I realized he was dying because of the fluid buildup. in his lungs, and I'm the one that called the doctor. And they said, well, can he wait until Tuesday? And I said, no, he's pretty bad. We need to bring him in now, and you probably need to do emergency surgery. There was somebody on call. It wasn't the doctor that was supposed to do the surgery, it was somebody else. Because, the doctor that was supposed to do the surgery was gone and wouldn't be back until Tuesday. Anyway, he was going to take a long weekend. As it worked out, everything worked out. My dad survived. They put in a pig valve in his heart, and lived until he was 90 years old. So everything's fine. Under cold conditions, the sympathetic nervous system stimulates metabolism within brown adipose tissue, producing heat. And of course, that's what we're trying to do. We're trying to produce heat. We're burning up the brown adipose tissue if we possibly need to, just to stay warm. Humans start shivering at about 36.5 degrees centigrade, that's 97.7 degrees Fahrenheit, which starts in the face and it spreads downward. If you've ever started to shiver, you can feel your cheeks start to palpitate, and then it moves down into your body. Other things happen. The hair on your arms and your legs and wherever you have hair will stand up. That's to catch more heat so that less heat escapes. That's another way that you can warm yourself. If you're ever really cold, you get what they call goosebumps. What goosebumps really are is just your hair standing up as straight as it possibly can to trap as much heat as possible. When the human body is hotter than is safe for the individual well-being, brain cells can very quickly be adversely affected if the temperature isn't controlled. The body can cool itself through accelerated respiration, panting, perspiration to cool the skin, dilation of blood vessels to release heat through the skin surface. Now you can take medications that will, you can take drugs that will look like that will make you look like you're too hot. You look like you're too hot. If you take ecstasy of course raises your body temperature, and some people, and you will start salivating. And the biggest problem that people who are using ecstasy and they don't know what they're doing, a lot of times these people will die of heat prostration. It's really kind of an interesting situation because their body temperature will increase so much and they start salivating, so they're losing water. And now we got a really serious problem because you're losing water and you're too hot. So if you've ever been any place near people that are raving, this is kind of an old thing that they used to do back in the 90s and the early 21st century. If you've ever been in that situation, then what will happen is they will have it in a warehouse or something, and they'll have the temperature turned way down so that the individuals won't die of heat prostration. If you've ever been around somebody that's taking ecstasy, a lot of times they salivate excessively. And because of that, what they will do is they'll suck on pacifiers, just like a little baby. And of course, they swallow their own saliva, and that keeps them hydrated. These individuals, a lot of times, they'll have to go out because they're dancing and they're hugging and all that other stuff. People on ecstasy. Anyway, they will. A lot of times, if they're not monitored by somebody, a lot of times it's like they have a fever. They will die. Not uncommon. The human body doesn't seem to have just one thermostat, but it has three. The hypothalamus in your brain, of course, in the middle of your brain, will tell you if you're cold or you're hot. The surface of your skin tells you whether you're cold or hot. Sometimes you don't have to pay attention to your skin. Sometimes you'll touch your skin and it'll feel cold. But you feel okay. And the reason you feel okay is because
As long as your body's core is nice and warm, then you're probably okay. Your body's core, if we look, this is your body's core, it's your thorax. And this is one of the reasons, if you've ever watched any of those television shows where the medical examiner will come and they'll say, well, when did he die? One of the things he will do is that he will stick a thermometer into the individual's liver, which is right about in the middle of your core, and he'll take the body's core temperature. There's a formula that they can use. If the ambient temperature outside is 75 degrees, how fast does the human body cool off? If it's like 10 degrees, it'll cool off a lot faster. But they have a formula that they use to determine how long an individual has been dead. And they usually can hit it right around, they can usually hit it within an hour or so. So what will happen on the television show, they'll say he died sometime between midnight and 1 o'clock in the morning. That's because his core temperature has decreased a select amount. If they've been dead for over 12 hours, then it's really difficult to tell how long they've been dead. Not from their core temperature, because the human body, of course, will cool off relatively fast, and once it gets to the ambient temperature, then it's almost impossible to tell the difference between when they died and when they were alive. As evolutionary biologists point out, humans have the same concentration of salt in our body fluid as the oceans of the world. It is therefore assumed that humans evolved from creatures in the sea who had to maintain a fluid and salt content similar to that of the sea. Thus, humans, as all animals, must not only monitor their fluid levels, but their salt levels as well. If I jump into a clear pool, a pool that is just water, it's not salt water, then if I started drinking that water, of course, I would get too much water in my system, and I would dilute out the salt, and then of course I'd be in trouble. I'd be in a lot of trouble. Osmosis is a special case of diffusion. In this case, a large molecule like starch is dissolved in water. The starch molecule is too large to pass through the pores in the cell membrane, so it cannot diffuse from one side of the membrane to the other. The water molecules can, and they do, pass through the membranes. Hence, the membrane is said to be semi-permeable. Some things semi-permeable means partially permeable. The water can go through, but the solid material cannot. So it makes it a semi-permeable membrane. It allows some things to pass through and others not to pass through. Except for deionized water, we talked about this last time, other forms of water that we might take into our bodies is in the form of a solution, a mixture of molecules of solid molecules and water molecules. So if you look at a water bottle, you think you're drinking water, but actually you're drinking water with minerals in it of one kind or another. Now, of course, we put special things in there like vitamins, vitamin water, or whatever. And potentially it doesn't taste any different. Most vitamins do have a flavor, of course, and sometimes it's not a very good flavor. So you have to mix it with something else. There's a new water out called Hint, where it has a hint of flavor to it. I guess watermelon is one of them. Anyway, the solid material in there is known as a solute. My water, this isn't really water, this is lemonade. I make lemonade, I drink lemonade, and I don't drink water because water has, because I can taste it, and I don't like the flavor of water. Also, water hits my stomach, and for some reason it creates a lot of acid. If I drink an acidic drink, it doesn't create a lot of acid. So usually I drink something that is fairly acidic, like lemonade. In order to make my lemonade, I mix water with Crystal light. Crystal light is, it's crystals, of course, hence the name, crystal light. And it's a solid. So what I will do is I'll take a select amount of water, 12 ounces of water, and I will mix it with crystal light. And as soon as you pour the crystal light into the water, the crystal light will dissolve. Well, when it dissolves and makes lemonade, that is, the crystal light is the solute and the water is the solvent. I also put half a lemon in all my lemonade just to give it a strong kick of lemon. So my lemonade's pretty sour, relatively sour. Flavor it to taste. I don't use regular water. I was warned about the water around here that it may be tainted with things that I won't like, such as uranium. So I mix it with canned water. Usually seltzer water, bubble water, Sprudelwasser, as they say in Germany. It's usually that. Sometimes it's flavored, lemon-flavored seltzer water that I use. That's my solvent. And of course it has seltzer in it, which is another type of solute. Semi-permeable membranes will block the passage of the solute but allow the water molecules to pass freely from one side to the other. The force or pressure to pull water across a semi-permeable membrane is known as the osmotic pressure. We refer to the concentration of solute in a solution as the solution's osmolality. We very rarely see a solution that is just water. It normally has some solute in it, depending on what it could possibly be, whether it's minerals of one kind or another, or whatever, or uranium, I guess. Sodium chloride is a solute that the human body must balance in order to maintain a proper fluid balance. The human body must maintain a proper level of sodium chloride in order to function properly. And of course, this was the problem with the slaves. Of course, they lived in a tropical area. They were being taken from one place to the other. Sometimes they were on the ocean for a week or two to get from Africa to the Americas. And they had very little water. So the ones who had strong salt content in their bodies, they required more water, and these individuals didn't survive because they didn't have any water to give them. But that was okay. Well, as far as the people doing the transporting, that was okay because they factored all of this into their profit margin. The human body must maintain a proper level of sodium chloride in order to function properly. That level of sodium chloride is 0.9%, or 9 grams of sodium chloride dissolved in a liter of water. And if you've ever tasted this stuff, it's pretty salty. That's the amount of salt water that is in the ocean. That's known as normal saline or isotonic. The isotonic solution is salt water. So when I was working in the laboratory, we would mix, if we needed to dilute somebody's blood, in order not to break down all the red cells and all the white cells, we would use an isotonic solution to mix with the red cells and white, to mix with the blood. If you do that, of course, you can actually mix, you can actually dilute out the blood without destroying the cells. But it had to be normal saline, it had to be an isotonic solution. And of course, isotonic solutions, to make sure that it's 0.9%, of course you'd have to buy it, and it was relatively expensive. And this stuff was known as saline or isotonic solution. If somebody came in who was dehydrated, especially if they were severely dehydrated and they needed fluids right away, we couldn't give them water. If we give them water, of course, it's going to dilute out the salt too much. So what we would do, we would give them an IV of saline, give them an IV of isotonic solution. If you give somebody water through the IV, it will adjust their osmolality in a negative in a negative manner. In other words, they won't have enough salt in their system. If you give them too much water, if too much water gets into somebody's system, their blood vessels will start to explode because they don't have enough salt. And this is known as a hypotonic solution. There's too much water, not enough salt. Their red blood cells will start to explode. They will become too full of water because the red blood cell has a semi-permeable membrane around it. If there's too much salt in the system, then the cell will collapse. And of course, the too much salt in the system is known as hypertonic. So it's either hypotonic, there's not enough salt, or hypertonic, there's too much salt. And this is what red cells look like. I worked in the lab for 30 years and I got to see lots and lots of red blood cells. Normally they look like, Normally they look like this. This is what a normal cell looks like. It looks like a donut. An inner tube. This isn't open, of course. The middle of it's not really open. It's a closed system. But if it's a hypotonic, if you see hypertonic, an individual in a hypotonic situation, the red blood cells look like big balls. And that's not a good thing. That's really a bad thing, because the next thing that happens is the red blood cell will explode, as you can see. It looks like a blown out balloon over there. If it's hypertonic, then the cell will collapse. If this is what it normally looks like, it will collapse. And this is known as a crenated red cell. It has collapsed on itself. And from time to time, especially with an individual that is dehydrated, you'll see some degree of crenated red cells. Now, the interesting thing about crenated red cells, sometimes if you can give them fluid fast enough, that cell will become a normal cell again. But sometimes they won't come back. So now the person has all these cells in their body that are non-functional, that will not carry oxygen to the brain. Now we got a really serious problem. There's not a whole lot you can do. Well, sometimes you can give them packed red blood cells in order to replace their red blood cells. Not normally what we will do. Normally what we do is we just let them go. And of course, well, they haven't died, and we've saved their lives, but eventually, of course, their body will clean out all those red blood cells that don't function. Red cells are living cells. They're just like any other tissue in the body. They last for about 200 days, which is kind of interesting. And you have a lot more than you actually need. And because of that, the body can function with crenated red cells. It can function with hypotonic red cells floating around in the system. It's just that you're not going to be able to run a marathon with either hypotonic or hypertonic cells in your system. The other thing that happens to people is sometimes they get around carbon monoxide. Carbon monoxide has an affinity for red blood cells, as odd as that may seem. So if you're breathing in oxygen and you're also breathing in carbon monoxide, the carbon monoxide is more likely to attach itself to the red blood cell. And if it does that, then that red blood cell cannot carry oxygen. And this is the reason that people, when they're around carbon monoxide, they get carbon monoxide poisoning and they die because the red blood cells will not carry oxygen anymore. This is kind of a serious situation. If we can start giving them pure oxygen, and if we can remove the carbon monoxide and give them straight oxygen, a lot of times we can bring them back. But like I said, they're probably not going to be running a marathon anytime soon. The human body is constantly replacing the red blood cells. They only last for about 200 days. So eventually, of course, in about about 6 or 8 weeks, they've replaced enough red blood cells that they're fairly normal after that. It's a really serious situation.
We can't allow this to happen, we can't allow this to happen, and we can't get around carbon monoxide. However, somebody who smokes cigarettes, especially in the old days, people were chain smokers. They smoked a lot of cigarettes. Cigarettes, of course, when the paper burns, you're breathing in carbon monoxide. And the individual was actually asphyxiating themselves, which is kind of an interesting situation. When I was in the service, we had a test for carbon monoxide poisoning. We had a test for carbon monoxide poisoning, and we would have to draw a positive control and negative control. We needed a positive control and a negative control. Well, there's no negative control out there. It has to do with breathing in carbon monoxide. So what we did, we had an individual who was a chain smoker, and we would use him as our positive control. And of course, I don't smoke, and I never have smoked, so they would use me as the negative control, and my friend as a positive control. It's really kind of interesting to see the difference between our red cells, or our blood, when we mixed it in a sodium citrate tube. Mine was purple and his was bright red, and that, of course, is positive. So we could tell if somebody had breathed in too much carbon monoxide by comparing it with his blood. Which is sad, because I mean, you would think that we're looking at this on a continual basis, and you'd think that he would go, maybe I ought to stop smoking, but he never did. And he died of lung cancer in his 50s. Internal cues that trigger thirst: hypovolemic thirst, thirst caused by low volume of fluid. Baroreceptors in the major blood vessels detect any pressure drop from fluid loss, usually caused by rapid loss of bodily fluids such as hemorrhaging, diarrhea, or vomiting. Strangely enough, the fastest way to lose fluid is through diarrhea. People don't realize that just because they've got the squirts, that they need to take in a lot more fluid because they're losing fluid at an excessive rate. Once upon a time, I was working this is when I was in the service. We had a 12-year-old girl that came in, and she had the most violent diarrhea that anybody had ever seen. So of course we started her on normal saline, started an IV in one arm. It wasn't enough. She was still just losing fluid at an excessive rate. So we started an IV in the other arm, testing her stool to find out what's going on. Is it a parasite? Is it bacteria? Is it dysentery? Is it tons of different things it could possibly have been. And it still wasn't working. We didn't find anything. We couldn't grow anything on her culture plates. The doctor was getting real antsy because he had to start IVs in both of her legs. Here we're pumping all this fluid into her. We're forcing fluid into this poor kid's body, and all she's doing is just squirting like crazy. And we couldn't figure out what it was that was causing her problem. We had a lady that was working in parasitology that didn't care. She hated the smell of feces, the whole thing. I mean, if you work in the lab, you work with really bad smells almost all the time. So you got to be used to it. You got to put up with it. And she just didn't want to look at the stools. She did, of course, and then she complained about it. Anyway, so I was in charge of the lab, and I went into micro, where we had parasitology, and I looked at her slide, and I couldn't see anything either. Looked like there were a bunch of white cells in there, but there was nothing else. You couldn't see any bacteria. Normally the stool was just packed with bacteria. Not this time. You couldn't see anything. So I thought, those white cells look a little funny. I wonder if they're yeast. So I did a germ tube on the kid's stool. Turned out that it was yeast. What had happened was they had treated the kid for They had treated the kid for a urinary tract infection, and they had given her a broad spectrum antibiotic, and for some reason it killed off all the normal flora in her digestive tract. So what happened, you take away all the bacteria, and all of a sudden the yeast, she just had this massive yeast infection in her gut. And normally you don't see this, nor, it wasn't in any of the literature, but it was causing her problem. So we gave her an antifungal. We gave her Flagyl, which is an antifungal medication, and it killed off the yeast. As soon as the yeast were dead, we gave her yogurt. The yogurt replaced her normal flora in her gut, and she stopped squirting. We were within hours of her dying. It was that bad because her diarrhea was that bad. We have a new way of treating diarrhea, as curious as that is. I'm sure you've heard about this. Usually diarrhea is caused by spasming of the digestive tract, and you have to stop the spasming. Well, the reason the digestive tract is spasming is because of electrolytes. You don't have enough electrolytes in the area. So what you do is, the new treatment is clear water and Gatorade. So the first time you give them clear water so that they have something to squirt out. And then the next time they're thirsty, you give them Gatorade. And the Gatorade, of course, has electrolytes in it, and it will replace the electrolytes that are missing. And usually it will stop the diarrhea in one or two bottles of Gatorade. It's really kind of magic, I guess. Anyway, that's how we're treating diarrhea. Diarrhea used to be the #1 killer around the world. The kids would get diarrhea, would just take a couple bouts of diarrhea, and they would be dehydrated and they would die. But now, of course, that we have Gatorade all over the place, we can give them Gatorade and we can save their lives. So hypovolemic thirst is one type of thirst. Osmotic thirst is another type of thirst. High volumes of solute in the extracellular fluid. Osmoreceptors in the brain detect any increased osmolality of extracellular fluid. So if you're taking in too much extracellular, too much solute in your liquid that you're taking, then you're going to feel thirsty. And it's one of the reasons why if you drink, if you don't drink water, if you drink something else, Gatorade usually is a pretty good thirst quencher. You can drink Gatorade, you can drink water, but if you drink something else like a Coke, there's too much stuff in there, and usually that stuff is sugar, and of course you haven't really taken care of your thirst. Or lemonade. Lemonade's got lemon in it, so potentially doesn't take care of your thirst. It does work for me, so don't worry about me. I'm okay. Hypovolemic thirst, when baroreceptors detect a drop in blood pressure from the tension on the artery walls. The information is relayed to the autonomic nervous system. The blood vessels constrict to maintain proper pressure for consciousness. The brain also releases vasopressin, antidiuretic hormone, from the posterior pituitary gland. Vasopressin acts on the kidneys to reduce flow of water to the bladder. And this is the reason why if a child is a bedwetter, sometimes we will spray vasopressin in their nose before they go to bed at night. And what we're really doing is we're reducing the water flow to the bladder so they don't wet the bed because they don't feel like they need to pee. Normally what will happen is they'll be okay that night, and then in the morning, of course, they'll get up and they still won't urinate a whole lot, and then all of a sudden, sometime around 9 or 10 o'clock in the morning, they'll just water will start flowing into their bladder and they'll have to urinate. In diabetes insipidus, vasopressin is not produced and the kidneys will not retain water. The patient is constantly thirsty, they drink a lot of water, and they urinate constantly. And if you look at their urine, it's almost completely clear because there's nothing in it. One of the things that we used to do when I worked in the laboratory is we would measure the osmolality of the urine. We would compare the urine to water. Water has 1.001 amount of solute in it, depending on how yellow your urine is. The yellower your urine, the more stuff that's in there. We used to see a lot of cloudy urine when I first started in the lab. Not so much anymore. People don't have cloudy urine anymore. It's because they drink so much. A lot of times they drink coffee, or they drink something with caffeine. Caffeine's a diuretic, and it makes them urinate a lot. And because of that, of course, they don't have a lot of stuff in there, any extraneous stuff, any extraneous solute in their urine. But if somebody has diabetes insipidus, of course, their urine is almost pure water. The kidneys also detect the low blood volume and release a hormone called renin. Renin triggers a protein called angiotensinogen to form the protein angiotensin 1, and in turn becomes angiotensin 2, as weird as that is. Now, so it has to go through this whole process. From renin it triggers a protein called angiotensinogen, and then it creates angiotensin 1 and then angiotensin 2. Now the angiotensin 2 is the substance, is the chemical that will change a lot of things. Angiotensin 2 constricts your blood vessels. It triggers the release of vasopressin. It triggers the release of aldosterone. It acts on the preoptic area of the brain to elicit the feeling of thirst, and it makes you want to drink. So all of these four things happen because of angiotensin 2. If you don't have angiotensin 2, none of these things take place. So let's say that we do produce the renin, we do produce the angiotensinogen, which triggers the angiotensin 1, but we don't ever get to angiotensin 2, so nothing happens. It has to be the angiotensin 2. Kind of a complex process for something relatively simple. This is accomplished in this subfornical organ, one of the circumventricular organs around the open areas of the ventricles of the brain where the blood-brain barrier are weak. And for that reason, of course, this is the area that we're looking at. Now this gets kind of funny. I guess it's not that funny, but the ventricles of your brain, these are the open areas in your brain, as strange as that may seem. These are the open areas of your brain. Now, if you are a schizophrenic, one of the things that happens to people that are schizophrenic is these areas, these open areas of the brain get larger. Osmotic thirst. Osmotic thirst is more common than hypovolemic thirst, and as the name suggests, it has to do with an imbalance of sodium chloride in the extracellular fluid due to loss of water. Osmotic thirst is caused by perspiration. If you sweat a lot, if you're breathing really hard, respiration, of course, you're breathing out water every time you breathe, or if you urinate a lot. What can cause you to urinate a lot? Well, if you have a lot of water in your system, you're going to urinate a lot. But sometimes you don't take in that much more water, and all of a sudden you're urinating a great deal. So what in the world is causing this? One of the things that can cause you to urinate is a lower barometric pressure. In other words, if a storm moves into your area, then potentially you're going to urinate more than you did otherwise, than you would have otherwise. So bad weather will cause you to urinate a lot, as strange as that seems. It's like as the barometric pressure goes down, it's squeezing the water out of your body. So last week
It snowed. I don't know if you remember when it snowed. It snowed on Sunday night, Monday morning. Anyway, I got up about 6 times during the night and urinated that night. Of course, it's not like I'm an average guy or something. But because the barometric pressure crashed, it forced all the fluid out of my body, and I urinated a bunch. I didn't feel thirsty. That was the bizarre part. I didn't really feel thirsty, but I was getting up and I was urinating volumes every time I got up. But it was because the barometric pressure had gone down so much. Since we are dealing with an increase of sodium chloride in the system, this form of thirst can be triggered by eating salty foods. So you could feel thirsty because you're eating potato chips or you're eating popcorn or whatever, and that'll cause you to want to drink something. Now, this is one of the reasons why everybody has to have popcorn at the movies. It's not so you get to drink a lot. It's a plan. In bars, they used to have pretzels on the bar. They used to have peanuts, and of course the peanuts were real salty, and the pretzels are relatively salty. Or they had popcorn, and they would give you the popcorn or the pretzels for free, or the peanuts, whatever, for free. And then of course, how in the world did you quench your thirst? You had to drink a beer or whatever. And so they would do this at bars. Well, they do the same thing in theaters. They have really salty popcorn, and you're going to need a drink to wash it down. To neutralize the amount of salt that you're taking into your body, so you need a Coke. So that's the trick. Osmotic thirst, research shows that humans have osmoreceptors in various areas in the preoptic area, the anterior hypothalamus, the supraoptic nucleus, the organum vasculosum of the lamina terminalis. These are all right in the front of your brains. Osmotic thirst, sodium chloride balance in the body is very delicate. As we have noted before, hypertonicity or hypotonicity will cause cell destruction, and this is very, very real. This is not, this can happen with a meal, and this is one of the reasons why you usually drink while you're eating, especially if you're eating relatively salty foods. When angiotensin II is released in the bloodstream, it acts on the adrenal glands to release the mineralocorticoid steroid hormone aldosterone. Aldosterone acts on the kidneys to conserve sodium, which in turn allows the individual to conserve water in the body. The more sodium you have in the body, the more water that you need to neutralize it. However, humans cannot drink seawater. It is hypertonic, and thus it adds more salt than water, causing greater thirst. And for this reason, if you are, your ship goes down and you survive the shipwreck, then potentially what you will have to do is you're going to have to drink fresh water. You can't drink urine. Urine is too hypertonic as well. You can't lick sweat off of your arms. That is also very salty. And you certainly can't drink the salt water, so you're going to have to find water someplace. While humans have not evolved to handle hypertonic conditions, creatures that live in the ocean or are able to survive with little water have kidneys that can handle large volumes of sodium chloride. So the Gila monster, any of the lizards that you see out in the desert where it's really, really hot, there's no water. So how in the world are they able to survive in that environment? Well, the reason they can survive is because their kidneys can handle large volumes of sodium chloride. Places where there is large concentrations of sodium chloride, a lot of times you don't see animals around those areas. But there are animals will come around to consume the salt. Deer, for example, will come around to consume the salt. Not only do organisms require water and warmth to survive, but they need food as an energy source. If this were the extent of our needs, humans could eat raw glucose and live very well. but we can't. There's not enough nutrients. You couldn't eat candy for the rest of your life and live very well. You're going to feed your cells fairly well, but fairly quickly your body would have a depletion of minerals and you would get sick and die. Humans also require nutrients, chemicals that do not provide energy, but are required for proper functioning of the body. So you need to take in these minerals every day. Usually we get all of these minerals from our diets. We eat a well-balanced diet, and because of that, we don't need to take in any supplements, but we do anyway. Some of the nutrients that we require are in the form of amino acids. Of the 20 amino acids required by the human body, 11 are manufactured internally, so we don't have to worry about them because we just manufacture them naturally. But there's 9 that must be attained through our diet, and these are known as the 9 essential amino acids. Now this gets to be a problem because one of these amino acids is in meat. We find in flesh. So how do we get this amino acid if we're a vegan? We can mix two foods together and we can create that amino acid. Usually it's from nuts. Besides the essential amino acids, our bodies require 15 vitamins, several minerals, and a few fatty acids from our food. So this is what we need to take in. These nutrients are obtained when the body breaks down complex foods into simpler forms through the process of digestion. And of course, if you've got a flaw in your digestive system, then sometimes your body will not be able to break down and absorb the right substances. I can't think of what it is. Anyway, we used to do a test for fatty acids. Some individuals, some children have a genetic flaw where they're not taking in fatty acids. And we can tell this by looking at their stool specimen to find out whether they are absorbing the fatty acids or not. And we used to do this by taking an X-ray film, and we would put their stool specimen on that film, and if it broke down the film so that it was clear, then it meant that they were breaking down, that they were utilizing the fatty acids properly. If we put it on there and it didn't eat away the covering of the X-ray film, then we knew that they had a flaw in their digestive system. Most animals, especially humans, will build up stores of nutrients in their body. This is done because of our anthropologic ancestors tended to go through cycles of feast and famine, and the individual who could not establish stores of excess nutrients, usually in the form of fat, would not survive to reproduce. And of course, then they would fall out of the gene pool, and then we didn't have to worry about them anymore. All the energy that we need to move, think, breathe, and maintain body temperature is derived in the same way. It is released as chemical bonds of complex molecules are broken to form smaller, simpler compounds. And the simplest compound that we're looking for is sugar. Sugar is, if we take something into our body and we can't break it down into sugar, then it's not food. That's why we can't eat plastic. That's why we can't eat, we can't eat bark. We can't eat wood. It's cellulose. Some animals can eat it and they can break it down, but humans cannot because we don't have the enzymes in our body to break it down into food. To raise body temperature, we release bond energy as heat. The amount of energy used is expressed in kilocalories. While not all foodstuffs provide energy, that which cannot be used is excreted, especially as solid waste. Available energy is used in one of 3 activities. Processing of newly ingested food takes up about 33% of our energy utilization. Basal metabolism, maintaining our bodies, takes up about 55% of our energy utilization. So the reality is, if we were relatively sedentary, we're not going to balloon out and become a massive person. What will happen
is that about 60% of our energy will still be utilized. So we can maintain ourselves in a relatively sedentary situation because 60% of all the energy that we use is used to maintain ourselves. We can only burn off about 12% of our energy stores through activity. So people that say, you need to diet and exercise, and other people say, no, you don't need to diet, all you need to do is exercise. Well, exercise only takes up about 12% of your energy. The rest of it's taken up in maintaining yourself. 33% has to do with breaking down your food. 55% has to do with maintaining your body. So you have to diet and you have to exercise at the same time. If you diet and don't exercise, of course, you're going to lose muscle mass, and you don't want to do that. The body uses glucose as an energy source, and so it breaks everything eaten into this form, as I said before. Glucose is stored in the body, in the liver, as a substance called glycogen. When ingested glucose is low, in other words, you're not taking in enough sugar, the body will release glycogen from the liver to keep the brain functioning. The release and breakdown of glycogen from the liver is controlled by two enzymes from the pancreas. The glucagon promotes breakdown of glycogen to glucose in a process known as glycogenolysis. Insulin promotes conversion of glucose to glycogen. Okay, there we go. So we need glucagon and we need insulin in order to maintain ourselves. If we are diabetic, of course, if we're type 1 diabetic, we're not producing insulin. If we're type 2 diabetic, it means that our body has become insensitive to insulin. And for that reason, of course, in order to maintain ourselves, we need to take a medication. We need to take something in order to survive. In the case of type 1 diabetes, we can take synthetic insulin to make ourselves function. In the case of type 2 diabetes, we take a substance known as metformin, and the metformin induces our body to utilize the insulin. When an individual has been without food for a prolonged period, either forced or due to dieting, they begin converting their adipose tissue into glucose in a process known as glucogenesis. Gluconeogenesis. At the same time, they will produce a secondary fuel called ketones, which can be used by the body and brain as fuel. One of the ways that you can tell if somebody is diabetic is if they have bad breath. Why do they have bad breath? Because they're putting off ketones. If somebody is diabetic, they also will not, if somebody is diabetic, they also will not be able to gain weight, because weight has to do with fat. Okay. Long-term energy stores are in the form of fat cells or adipose tissue. Adipose tissue can be used for energy when the ready amount of glucose in the system has been depleted. Adipose tissue can be broken down into its simpler forms, fatty acids, and glucose. Glucose is brought into individual cells through glucose transporters in the cell membrane. Glucose transporters can only function when they interact with insulin. And there's the reason why type 1 and type 2 diabetes exists. Except for brain cells which do not need insulin to function, otherwise diabetes mellitus would cause such severe brain damage that it would be instantly deadly. And for this reason, of course, since the brain cells don't need insulin, a diabetic has no brain damage, despite the fact that it looks like potentially, of course, they would have a very serious problem. There are three phases that the body must go through to be able to utilize glucose in the diet: the cephalic phase, the digestive phase, and the absorptive phase. The food itself acts as a stimuli.
Sight, smell, and taste of the food will induce us to want to digest food. This evokes a conditioned release of insulin in the anticipation of glucose arrival in the blood. All we have to do is see it, we have to smell it, and as soon as we taste it, of course, we start producing the insulin. And now our body is ready to digest the food. At this phase, the release of insulin is regulated by the brain and is thus referred to as the cephalic phase, because we see the food, we smell the food, we taste the food, and now we release insulin because of that. In the digestive phase, food entering the stomach and intestines causes the release of gut hormones. This stimulates the pancreas to release more insulin. During the absorptive phase, glucose enters the bloodstream and special cells in the liver. The glucodetectors or glucostats detect circulating glucose and signal the pancreas to release more insulin. And that is so that we can utilize those energy stores in all of our cells. Insulin allows the body to either utilize glucose immediately or convert it into glycogen. If we take in more sugar than we can utilize right now, then we will convert that extra glucose into glycogen. The nerve that passes information from the liver to the brain and back to the pancreas is the vagus nerve. And this is right in the middle of your body, and it's really protected. It's a nerve that tells your body tells your heart to beat, it tells your body to function. The vagus nerve runs to the nucleus of the solitary tract in the brainstem. Diabetes mellitus is the lack of insulin causing a disease called, the lack of insulin causes a disease called diabetes mellitus. As I said before, there's two types. Type 1, which we used to refer to as juvenile onset diabetes mellitus. In this case, the pancreas stops producing insulin. Used to be because of a genetic flaw or some other problem. We used to only see this in newborns, in children. We rarely saw it in adults, but now we see people in their 20s and 30s, teenagers developing type 1 diabetes. I had never seen this before, but within the last 20 or 30 years, this has become relatively commonplace for people to develop type 1 diabetes. Though the brain can still utilize the glucose from the diet, the rest of the body can't, and so it utilizes fat stores instead. And this is why when somebody comes down with type 1 diabetes, they get skinny. They get really, really skinny because their body cannot produce, it isn't producing any more fat, but it doesn't have the insulin it's not producing the insulin, so it's not producing any more fat. Remember, it's insulin that tells the liver to start storing glycogen, I'm sorry. Since most of the dietary glucose cannot be used, it passes through the system and is excreted in the urine, and for that reason you have a high sugar level in your urine. Glucose can also not be converted to glycogen and stored in the liver. Diabetics are hungry because the body tells them to consume energy, but they can't gain weight because they do not store glucose as fat. Treatment is to provide exogenous insulin. In other words, it's synthetic insulin. We used to use insulin from sheep. That was the first synthetic insulin that we had.